Hello, my name is Gustav Vogels. I am an electronic technician. My profession is the development of electronic systems. First of all, I would like to apologize for my poor English. I've lived my whole life in Germany and I only learned English at school, but that was around 60 years ago. I definitely don't want to present another new story or tale about Bletchley Park, Alan Turing or Gordon Welchman in this YouTube post. These are all very interesting places and interesting people, but my lecture is all about the decryption method of a ciphertext from a German Enigma. This decryption method, mainly developed by Alan Turing and Gordon Welchman, I will describe and explain in detail in this lecture. I don't leave anything out, I don't hold anything back, and I don't skip anything in the decryption process, and I reveal even the smallest detail. This is certainly not as entertaining as other posts on the Turing-Welchman-Bomb. This lecture is only interesting for guys and smart girls who want to know how the British cracked the German Enigma. This post won't intimidate you with astronomical numbers telling you the whole thing is so difficult that you don't understand it. If you can think logically and understand the circuit diagram of a flashlight, you have all the prerequisites needed to understand the Enigma decryption process. This post also dispenses with spectacular images of war and dramatic background music. No prior knowledge of the function of the Turing-Welchman bomb is required for this lecture. The absolute prerequisite for understanding my lecture is that you have already understood how the Enigma works. In order to understand the decryption process of an Enigma ciphertext, one must first know how the Enigma encrypts a plaintext. The functionality of the Enigma is clearly explained in many places here on the internet. People who don't know how the Enigma encrypts plaintexts cannot understand how these texts were decrypted again with a method mainly developed by Alan Turing and Gordon Welchman. I would like to use an example to explain step by step how a German Enigma ciphertext message which the Briton intercepted was broken and how the settings of the Enigma used were found out. I will not only explain every single step of the decryption process of an Enigma ciphertext in detail, but I will also prove the correctness of each of my statements with my self-made microprocessor machine. This device can simulate the Turing-Welchman-Bomb, the Enigma, and other functions of the decryption process. Here you can see the device from the front. Here the text display. Here the keyboard. Here the lampboard that is needed to simulate the Enigma. Here you can see the other keys that are required. The window key, the input key and the output key, the printer key and the delete key. Here the input block. Here you can see the back of the device. Here is an insight into the interior of the device with the back removed. My simulation device simulates an Enigma with 3 rotors called M3. For this type of Enigma there were 5 different rotors that were used. Rotor Roman 1, 2, 3, 4 and 5. However, the basic procedure of this decryption process applies to all Enigma variants. There are people who believe that an Enigma ciphertext was somehow entered into the Turing-Welchman-Bomb and then somehow after a while the plain text come out of the Turing-Welchman-Bomb. That is the greatest mistake in understanding the Turing-Welchman-Bomb. A decryption of an Enigma ciphertext was not pretty easy. It takes a lot of steps to do. This lecture is also not intended for easy entertainment. On the contrary, it is hard to digest subject matter. The working of the Turing-Welchman-Bomb is only one part of this decryption process. It takes a lot of steps more. It is also not as shown in the film The Imitation Game, that a single ingenious idea was enough to solve the problem. Many ingenious ideas brought the overall solution here. Work in Bletchley Park was not based on the principle of ingenious ideas were then implemented, but worked according to the principle of trial and error. One should not only praise the skills of all the employees in Bletchley Park, but above all the persistence and the consistency in how this work was carried out. Understanding and emphasizing with all these works is, in my opinion, not easy. Anyone who raves about quick and easy solutions will not like this lecture. Anyone who claims that the great mathematics was necessary for the decryption process is lying. The basic arithmetic operations are sufficient. What is absolutely necessary is logical thinking. I repeat here again, if you don't know how the Enigma works, you can't comprehend my lecture and you can't understand what I'm talking about. This is fundamental up to now. Now I come to the decryption method that was used in Bletchley Park. The Polish cryptologists around Marian Rejewski already had solved Enigma ciphertext messages, but only because the Germans made a big mistake. They always sent the initial positions of the rotors twice. That opened up the possibility of decryption the messages. The Germans recognized that and changed the procedure. After that, the Poles could not longer decipher the Enigma messages of the Germans. It must now be said explicitly here. The British used a completely different method for the decryption. The credit for the developed decryption method therefore belongs to the British alone. The Enigma was from 1920 to 1928 freely available on the market and anyone could buy it. Due to this fact, the basic encryption method of the Enigma was well known before its military use. Anyway, the British knew also the wiring of the rotors by 1939 at the latest. By the way, it should be mentioned that the British modified their own cipher engine, Typex, so that the Enigma could be simulated with the Typex. So the British were able to examine and study the functionality in detail. The British received Enigma messages from the Germans from mainland Europe. Due to the signal strength and the direction of the signals, the British were able to draw conclusions about the transmitter stations. They knew the transmitter stations of the military headquarters and the weather stations. I have to say it here once. I adore Alan Turing and Gordon Welchman, and I don't want to forget the other stuff either. It wasn't the mathematical genius of these people, but their ability to think logically in order to solve the problem. Away with all the myths told and toward the logical procedure. The Germans change generally the Enigma settings once a day at midnight or during the night. The authorized recipients of Enigma messages had top secret key lists with the current settings of each day distributed in advance. In order to be able to decrypt every Enigma message of a day, the following settings are required. The wheel order, in German Walzenlage. That means which rotor was used in which place. The ring settings, in German Ringstellung. That was the ability to adjust the alphabet ring relative to the rotor disk. The Blackboard settings, in German Steckerbrett, according to the rules of the German army from August 1939, exactly 10 plug connections had to be made. The reflector settings, in German Umkehrwalze. With a few exceptions, the reflector B was always used in the 3-rotor Enigma. The starting position of the 3 rotors at the beginning of an encryption process, the so-called Grundstellung in German, changed with each new Enigma ciphertext message. These adjustments were made with the grooved finger wheels protruding from the closed lid of the Enigma. You can read these settings in the 3 small windows. All Enigma messages, including those in the course of a day, had their own start positions. There were no uniform starting positions within a day. That is why it was clear to the employees in Bletchley Park from the start that if you wanted to read the Germans' Enigma messages within a day, you had to have the same informations in the key list as the Germans. The seemingly impossible should come true. I would like to start with Alan Turing's first brilliant idea. Alan Turing recognized the construction flaw of the Enigma, which enabled the entry into the deciphering of Enigma ciphertext messages. The reflector gave Enigma the property that no letter ever encrypted to itself. Here's an example. At one place of the intercepted encrypted Enigma ciphertext message was the letter A. That means in plaintext the letter B to Z can appear here, but absolutely never the letter A. Alan Turing also knew the following characteristic regarding German Enigma messages. In German, military language usage were often repetitive idioms and repetitive sentences. An example was the beginning sentence of the weather forecast report. Some other Enigma ciphertext messages started with the sentence Das Oberkommando der Wehrmacht gibt bekannt. That means in English, the Wehrmacht High Command announces. The brilliant idea was to look for such sentences or formulations in Enigma ciphertext messages. It is first examined whether an Enigma message begins with such a sentence. But first you have to know the following. The German Wehrmacht used special terminologies, unusual abbreviations and some conventions which are not used in common German, such as representing the frequent bigrams CH and CK by a single letter Q. Next, there is no space between words, and punctuation marks such as a period are replaced with an X. Here's an example. It is assumed that the Enigma message begins with the sentence Das Oberkommando der Wehrmacht gibt bekannt. However, this sentence was presented differently in an Enigma message, namely as follows. You see, there are no free spaces. The letter combination CH became the letter Q. And the sentence ends with an X. In the next step, the presumed sentence is compared with the series of letters in the intercepted ciphertext message. When looking at the sentence with its 38 letters and the encrypted variant opposite, you can see that no single letter was encrypted in itself. The assumption that the intercepted and encrypted row of letters stands for the sentence Das Oberkommando der Wehrmacht gibt bekannt is correct with a probability bordering on certainty. The proof is that not a single one of these 38 letters has been encoded in itself. Coincidence is extremely unlikely here. A whole sentence has now been searched for here. Yes, it is true. You can only search for one word like Wehrmacht or weather forecast and so on. But this means looking for a needle in a haystack. It is more efficient to search for sentences or word combinations. After 26 letters at the latest, the middle rotor of the Enigma is advanced. The example sentence has 38 letters. At some point in this sentence, the middle rotor must have been advanced, but you don't know where. So long it was searched for a section in the text without advancing the middle rotor in which the decryption process works. The whole thing works on the principle of trial and error. If it doesn't work in one place, you have to try another place. In no case may this section have more than 26 letters, because in no case may the middle rotor advance. A useful number of letters are 10 to 18 letters. If there are fewer than 10 letters, it is seldom possible to create a loop. I will explain later what a loop means. If there are more than 18 letters, there is a high risk that the middle rotor will be advanced. The British called the series of letters to be searched for CRIP. Something is very important. This CRIP does not have to be a word in the linguistic sense. The search engine doesn't care. In the example in my lecture, I selected a CRIP with 15 letters from the sentence with its 38 letters. This CRIP is called Kommando der Wehr. Here is the section of the presumed Enigma message. Here is the opposite encrypted intercepted section of the Enigma ciphertext message. I hope that within this CRIP there is no advance of the middle rotor. If so, I'll have to choose a different CRIP in a different place. We will find out later. I am now typing the CRIP into my search engine. My search engine limits the number of letters for a CRIP to 20 letters. So far I have described what to look for. Now I would like to describe the search method used in Bletchley Park. But first I must say something about the rotors. There are 5 different rotors for this Enigma type M3. They have the Roman names 1, 2, 3, 4 and 5. 3 of these 5 rotors are placed in the Enigma. This means that there are 60 different ways for the choice of the rotors and the order in which they are fitted. This is called wheel order, or in German Walzenlage. Each rotor can turn in 26 different positions for the letters A to Z. Since 3 rotors are used in the Enigma, that means a total of 26 multiplied by 26 multiplied by 26. The result is 17,576 positions for the 3 rotors. These 17,576 positions multiplied by the 60 wheel orders result in a total of 1,054,560 possible positions for all rotors. I call these 1,054,560 possible positions of all rotors permutation addresses. This further means that there are 1,054,560 starting positions for a crypt. In my lecture, I will designate the possible start position of a crypt from Roman 1, 2, 3, A, to Roman 5, 4, 3, Z. In reality, it is less because, for example, the last position cannot be the start address for a crypt because nothing more comes after the last address. Due to the mechanical construction of the Enigma, some positions are also skipped. After that, there are a little less than 1,054,560 options for the starting position of a crypt. For the sake of simplicity, all 1,054,560 positions are processed in my microprocessor-controlled search engine. I would like to describe the structure of the Enigma rotors in a simplified manner as follows. There were 2 different versions of the rotors. Some have an alphabet ring, others have the numbers 1 through 26 printed on them. In this example, I assume that letters are printed. A rotor has an alphabet tire or lettering attached to the outside of the rotor disc. As I said, there are versions where the letters A to Z can be seen, and there are versions where the numbers 1 to 26 can be seen. One of these 26 symbols or signs is visible through the window for that slot in the cover, thus indicating the rotational position of the rotor. You have to imagine this lettering like a pot. The advanced power of a rotor acts on this pot. Transfer notches on this pot ensure that the next rotor will be advanced. The transfer notches are rigidly connected to the pot and their position cannot be changed. This means that the letter at which the next rotor will be advanced is different for each of the 5 different rotors, but always in the same place or always with the same letter on each rotor. After insertion, a rotor can be turned to the correct position by hand using the grooved finger wheel which protrudes from the internal Enigma cover when closed. In this spot, with the alphabet ring, there is an inner ring on the same axis. I've marked this inner ring in red. This inner ring in the pot contains the wiring of the rotor and the electrical contact pins. A special construction of these rotors is that the inner ring of these rotors can be moved up to 25 positions relative to the pot. This inner ring with its wiring can be postponed up to 25 positions compared to the alphabet ring. The 26th position, the position A or 1, means that there is no postponement. This inner ring is locked with the alphabet ring using a mechanical device consisting of a clip and a small bolt. The rotor Roman 1 has its transfer notch at the letter R. The rotor Roman 2 has its transfer notch at the letter F. The rotor Roman 3 has its transfer notch at the letter W. The rotor Roman 4 has its transfer notch at the letter K. And the rotor 5 has its transfer notch at the letter A. Which wiring works electrotechnically depends on the position of the alphabet ring, and it also depends on the position of the inner ring. The electrotechnically active position, depending on the alphabet ring and also on the inner ring, is what I refer to this lecture as the imaginary electrical active rotor position. I will come back to the relationships between the rotors with their alphabetical rings, the positions of the inner rings, and the imaginary electrically acting rotor positions later. Until then, it is very important to know that when I speak of the permutation address, I always mean the imaginary electrically active rotor position. Now I come back to the example in my lecture with the crypt Kommando der Wehr. The first letter K in this crypt is converted to the letter S in the absolutely correct start address. But with more than 1 million possible addresses, there will be many more addresses where a K is also randomly converted to an S. These additional addresses are then all wrong, and this explains the principle of the search in the whole process. The correct address is not searched for, but the incorrect addresses are excluded. At this point, Alan Turing had his next brilliant idea. The Enigma is a serial system. One after the other is encrypted letter by letter. Alan Turing had the idea to arrange several enigmas one after the other. Each downstream enigma is one address further than the previous one. With such an arrangement, one can examine not just a single letter, but a whole series of letters. This was the hour of birth of the Turing-Welchman-Bomb. First, we have to imagine an enigma that does not have a blackboard. The encryption is now carried out exclusively via the Enigma rotors. Instead of the Enigmas, 3 drums connected in series were used here. These 3 rotors connected in series simulate an Enigma and are called scrambler. With 15 such scramblers you can examine the row of letters with 15 letters that I use as an example in my lecture. It should also be mentioned in passing. In contrast to the Enigma, a scrambler has separate paths to and from the reflector. This is why the drums of the Turing-Welchman-Bomb also have 104 electrical contacts instead of 52 contacts as in the Enigma. The scramblers and the Enigmas also worked bidirectionally. This means that if an X is converted to a U in a scrambler, conversely a U is also converted to an X. With 15 such scramblers connected in series, one could check directly under which starting position from the ciphertext section the crypt Kommando der Wehr is converted. This method is called brute force attack. However, this method cannot be used because of the Blackboard. However, Alan Turing has dealt intensively with the brute force attack and considered whether he could use it in a different form. The whole thing had to be realized with the mechanical and the electromechanical means available at the time in the early 40s. One has to consider that since method brute force attack could not be used because of the Blackboard, one had to come up with something different. With the Blackboard it was much harder to decrypt Enigma ciphertext messages because it was unknown what the crypt and the ciphertext letters were transformed to by the Blackboard. The letters on the scramblers are completely different. The Blackboard offers countless more encryption options. At first the Blackboard seemed insurmountable. Anyone who has ever dealt with mathematics knows absolute and relative numbers. Here Alan Turing thought, if you can't determine the absolute letters as the scramblers, maybe it's about the relative relationships of the letters to each other. In relative terms, the only relevant thing is whether letters on scramblers are the same. Which letter is involved is initially completely uninteresting. He looked at these 2 rows of letters of the crypt and the opposite ciphertext section and had an inspiration that is awesome. He only looked at the letters in terms of their equality. Then he makes connections between some of the same letters. Sometimes it results in loops, as in my example here in my lecture. If you connect these 4 scramblers with 26-pin cables in the manner of letter O with O, letter R with R, letter T with T, and finally letter E with E, and the whole system is energized, this loop remains de-energized. At the mechanical Turing-Welchman-Bomb, a currentless loop is detected electrotechnically, and in this case the search is interrupted. A search engine should then not search for letters or text, but only for the graphical construct of the loop. Alan Turing's search engine should only look for such loops. As a reminder, the letters in this row stand for the keys pressed one after the other on the Enigma when creating the Enigma ciphertext message. The letter in that row represent the lamps in the Enigma's lamp board that flashed one after the other when these letters were typed. Here is the loop. I create a template based on this loop. I'll need the template in a moment. As an aside, I would like to say that a loop must contain at least 3 letters. But how is this template useful on the scramblers? I would like to remind you that the British, with the help of their modified typex engine, were able to check every part of the Enigma function down to the smallest detail. So they were also able to look at the letters on the rotor unit or on the scramblers unit during the permutation process. Letters are swapped by the Blackboard on the way from the keyboard to the rotor union, and letters are also swapped on the way from the rotor unit to the lamp board. However, these changes are always rigid during the entire process. According to the regulations of the German military, 20 letters of the 26 letters had to be swapped with the Blackboard. That means that 10 cables had to be plugged in. I would now like to show what the results from this. I have already anticipated the absolutely correct rows of letters on the scramblers when typing the crypt Kommando der Wehr into the Enigma. These are the letters from the keyboard with the Blackboard downstream. These are the letters from the scramblers with the Blackboard connected to the lamp board. In the middle are the letters that apply to the scramblers. I now place the loop template to these 2 rows of letters. I start the loop at the scrambler 8. These are the letters that are on the scramblers. You can clearly see that there are now different letters within the loop. But you can also see that the same loop can be created with these completely different letters. Alan Turing's key finding here is that if you can create a loop using the letters in the crypt and the letters in the ciphertext section opposite the crypt, you can apply this same loop on the scramblers as well. In these searches, according to Alan Turing's method, the correct 2 letters on a scrambler is initially of no importance. Rather, it is only checked whether you can form a loop with these letters. I would like to explain such a process in which a loop can be formed in detail and precisely using the example in my lecture. You know the shape and the course of the loop, but not the letters on the scramblers. In this example, the loop has 8 loop points. One of these 8 loop points is selected at the start or the entrance. This point is also known as the input letter. It doesn't really matter which of the 8 loop points is selected, but you have to stick to it during the decryption process. I do it so that I always start with the first loop point in the crypt. Since I don't know the letter at this input loop point at this scrambler with the absolutely correct solution, I have to search for a loop with all possible 26 letters of the alphabet. This means that for the 1,054,560 permutation addresses to be processed, already described, all letters of the alphabet must be processed per permutation address. In a complete search process for an Enigma with 3 rotors, 1,054,560 multiplied by 26 possible input letters are carried out. This in turn means that the Turing-Welchman-Bomb has to process 27,418,560 possibilities for a complete search process. In my example here in my lecture, this means that it must be checked among all 27,480,560 permutation addresses whether a loop can be formed according to the created pattern. In concrete terms, in this example in my lecture, this means that all 1,054,560 permutation addresses are proceed one after the other. For each of these 1,054,560 permutation addresses, all possible 26 letters are successively applied to the scrambler that was selected as a loop input letter. The mechanical Turing-Welchman-Bomb did not automatically process the 26 possible input letters one after the other, as I do with my microprocessor-controlled search engine. On the right side of the mechanical bomb are keypads with many switches that were used to select the input letters. Let's come back to my example in my lecture. The scramblers 8, 11, 13 and 10 are connected with 26 pin cables. As already said, the mechanical search engine looks for countless loops. The microprocessor version of the search engine searches as follows. I turned the connections on Scrambler 8 around. As already mentioned, scramblers worked bidirectionally. The letter that is applied to Scrambler 8 as an input letter is converted by it. The converted letter is then applied to scrambler 11. This converts the letter again. The newly converted letter is then applied to scrambler 13. This converts the letter again and places this converted letter on scrambler 10. Scrambler 10 also converts the letter. If this converted letter at the other end of the scrambler 10 is the same as the input letter, a loop could be formed. The insight here is that all 1,054,560 permutation addresses are processed. All 26 letters of the alphabet are tested as input letters under each permutation address. If the last letter of the last scrambler is the same as the input letter, a loop can be formed. The search engine wants to stop. The result here is that most permutation addresses cannot be looped. These permutation addresses are excluded. One of the permutation addresses under which a loop can be formed is the absolutely correct permutation address. All other permutation addresses under which a loop can be formed are random loop formations. Whenever a loop can be formed, the search engine wants to stop. With the microprocessor variant of the Turing-Welchman-Bomb I built, all 27,418,560 calculations are carried out. That means that all possible 60 rotor arrangements are tested with all possible 17,576 rotor addresses, and that with all 26 input letters of the EBC. So far I have explained what to look for and how to search. Now I would like to describe how such a ciphertext message from an Enigma is structured. One has to imagine the British intercepted an Enigma ciphertext message sent by the Germans. Such a message is called Funkspruch in German language. Such a Funkspruch is structured as follows. First, the header appears here. The first 4 numbers represent the time of the message sent. The second group of numbers represent the number of letters in the message. In this case, that's 204 letters. Then 2 rows with 3 letters each appear. These 2 times 3 letters are also called fictitious Rotors letters. The German operator of an Enigma was called Schlüsseler. The Schlüsseler has already set up his Enigma according to the specifications that apply for that day. He took these instructions for setting up the Enigma from the top secret key sheets, in German Schlüsseltafeln. Among other things, also with the correct ring settings. The Schlüsseler uses 3 made-up fictional letters that he chooses himself, made up not from any list, It's like rolling three letters. These letters are B, P, F. The Schlüssler uses these three chosen letters as the starting position of the rotors, in German language called Grundstellung. In the example in my lecture, these are the letters B, P and F. The Schlüssler then adjusts his Enigma with the grooved finger wheels. Then the Schlüssler uses three more made-up fictional letters, which he also chooses himself. These other three made-up letters are the letters W, N and I. These three letters W, N and I are also the three letters of the starting position for the Enigma ciphertext message to be encrypted later. Now he types in these three letters W, N and I, one after the other. He observes the lamp board while typing and sees how the lamps M, I and J light up one after the other. He notes these three letters. These six determined letters B, P, F and M, I, J here in the example in my lecture I now enter in my microprocessor-controlled search engine. These two groups of letters B, P, F and M, I, J can be found here. The Germans believed this would not be a problem because the enemy does not know about the ring settings and the other settings. Without the ring settings and the other settings, these two groups of three letters each were completely worthless to the British or other enemies. That is how the Germans thought. Then the message is divided into groups of 5 letters each. The first 5 letters of an Enigma message, which were also sent unencrypted, stand for the Kenngruppe. Put very briefly, the Kenngruppe says for whom the following message is intended. Because this part has no meaning for the decryption process of the Enigma message, I will not go into it further here. Then the actual Enigma message follows. The real message has 199 letters. To start my microprocessor-controlled search engine, I first have to enter the entire intercepted ciphertext into the machine. If I try to start the search engine without entering the ciphertext or without entering the crypt, I get a message on the display. According to Alan Turing's specifications, a search engine was then constructed and built at the British Tabulating Machine Company under the direction of Harold Keane. This prototype was called Victory. After the first test runs, it turned out that on one hand, the fundamental trains of thought of Alan Turing were correct, but on the other hand, they did not lead to the result that everyone had hoped for. Even if loops with 6 or more loop segments could be formed, which is extremely rare in practice, the search engine stopped too often. The reason for these stops are the random loops formations. It just took too much time to check all of these stops. The disappointment was very great. Alan Turing was very frustrated and couldn't think of anything else that could help. Now was the time of Gordon Welchman's big entrance. In the movie The Imitation Game, his name is not even mentioned. What a shame! Without Gordon Welchman, there would be no Turing-Welchman-Bomb. Without the Turing-Welchman-Bomb, there would be no movie. In my opinions, Gordon Welchman deserves as much honor as Alan Turing. What was Gordon Welchman's brilliant idea? We'll take my example again in my lecture. When the search engine is running, there will be numerous random stops, but also the absolutely correct search engine stop. We want to take a closer look at such a random stop. In this row are the letters of the crypt. These are the letters that the German Schlüsseler typed into his Enigma one after the other. In this row are the letters of the intercepted ciphertext section. These are the letters of the letter lamps that lit up one after the other on the Enigma as the text was entered. Without the idea and without the invention of Gordon Welchman's diagonal board, the search engine would now stop because a loop can be formed according to the loop template. The letters in the loop are wrong, but they form a loop, and because that is the case, the search engine wants to stop. I have marked letters that are not relevant with a question mark. The result of this attempt to stop is that here, 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 and here, the connector pairs of the Enigma's Blackboard show up. Imagine the letter K on the scrambler 2 at this point. This would mean that the letter O and K were swapped on the Enigma's Blackboard. Here on the scrambler 8, the letter B is at this point. This in turn would mean that the letters O and B on the Enigma's Blackboard were swapped. There is either a plug connection with the letters O and K on the Blackboard of the Enigma, or there is a plug connection with the letters O and B on the Blackboard. Both are not possible. Now, here is a contradiction. This is an example of what the German-Wehrmacht diagonal board does. It recognizes such contradictions and thus prevents unnecessary search engine stops. But before I get into that, I have to explain the following. I have already described that the 4 scramblers in the example in my lecture have to be connected with 4 cables with 26 pins each, so that you know which scrambler need to be connected to each other. You need to know how to plug up the Turing-Welchman-Bomb. To create such a Blackboard menu, the British have come up with a method that is very efficient. This method does not change the facts at all, but makes these relationships easier to understand. I would now like to explain this method with the help of small wooden sticks. Each small wooden stick represents a single scrambler. Since the crypt contains 15 letters, there are also 15 small wooden sticks. There is a letter on each end of the small wooden sticks. One letter comes from the row of letters of the intercepted Enigma ciphertext message section. The other comes from the row of letters of the assumed crypt. Here the letters of the crypt. The letters that are upside down here are the letters of the ciphertext section. In the middle on the small wooden sticks is the permutation address under which the permutation takes place. Similar to a puzzle, I now arrange these small wooden sticks in such a way that the ends of the small wooden sticks with the identical letters butt against each other. Please watch what I'm doing now. If I proceed according to this principle, the already known loop will automatically develop accordingly. The loop consists of 4 segments and 4 letters. I personally call the small wooden sticks, which can only dock onto other small wooden sticks with only one letter, boomers. If there are 2 or more small wooden sticks with the same letters on their ends, they can be removed except for one small wooden stick. Four small wooden sticks cannot be used. They no longer have any function during further processing. The result means for the scramblers, 4 scramblers are in the loop, and total of 6 boomers can be docked. This graphic representation now also shows which scrambler have to be connected to which other scramblers in the Turing-Welchman-Bomb. This is the plug-up menu. I drew the result as a diagram on a sheet of paper. It's the same diagram as one with the little wooden sticks. The simple diagram of a loop has now been expanded. As a reminder, it takes 15 scramblers to process the crypt in this example here in my lecture. They are numbered from left to right, 1 to 15. On this sheet, the diagram is shown with the letters at its corner points. In this same diagram, instead of the letters, I have written the numbers of the scramblers among which the permutations take place. As a reminder, the first letter in the crypt is processed by scrambler 1. The 15th letter is processed by scrambler 15. This is also the arrangement list for the cable connection on the back of the mechanical Turing-Welchman-Bomb. If the search engine tries to stop because a loop can be formed, letters will also appear at the corner points of the boomers. These letters must now be checked for plausibility. This plausibility check is carried out as follows. Here the diagram with the letters determined by the crypt and the opposite letter section of the ciphertext. Here is a diagram with the letters on the scramblers that result when the search engine tries to stop. The comparison of the corner points of the two diagrams show the plug connections made or not made on the plugboard of the Enigma. The letter A is swapped with the letter R. The letter M is swapped with the letter K. The letter K is swapped with the letter M. The letter E is not plugged. The letter O is swapped with the letter B. The letter S is not plugged. The letter T is swapped with the letter Z. The letter R is swapped with the letter A. The letter W is swapped with the letter P. And the letter J is swapped with the letter L. Here is another example. Most of it is the same as the previous example. But at this corner point on this boomer, there is a letter A. This means that the letter J has been swapped with the letter A on the blackboard. But here you can see the letter A has already been swapped with the letter R. But only one plug connection is possible. The letter A cannot be swapped with the letter R and also with the letter J. This is implausible and represents a contradiction. Such contradictions must be recognized and prevent the search engine from stopping. The question is, how do you recognize such a contradiction? As I have already said, with their modified typex machine and case studies they created themselves, the British were able to examine everything down to the smallest detail. Let's imagine the British had examined the example here in my lecture more closely with such a modified typex machine. Since the British would then have put the plugboard connections on the plugboard themselves, they would also have known the letters on the scramblers. Here are two diagrams on one sheet. The left diagram is divided from the crypt and the letters of the ciphertext section opposite the crypt. The diagram on the right is divided from the letters that are applied on the scramblers when the search engine tries to stop, due to a loop formation. The great achievement of Gordon Welchman is that he created the following rule for comparing the two diagrams. The rule is that no letter that is in this diagram may also be in that diagram. There are two exceptions, however, and they are crucial. In order to be able to show that better, I have arranged the letters facing each other in a comparison table. Each letter in this column is compared to each letter in that column. If the comparison shows that the letters are the same, you will be asked whether one of the two exceptions can be used here. The first exception is if the two same letters are at the same height in the comparison table, as is the case here and here, the rule made does not apply. The second exception is two letters are opposite each other at the same height in the comparison table. The same letters are opposite each other at a different height in the comparison table, but in reverse order. If that's the case, the rule does also not apply. If there is a letter in the left column and there is the same letter in the right column, and the two exceptions to the rule cannot be used, the diagonal board circuit ensures that the search engine does not stop. In this example, you can see that there is no contradiction. The rule with its exceptions is strictly adhered to. The circuit idea of the diagonal board was realized by Harold Keane from the British Tabulating Machine Company and then used in the bomb construction. With this diagonal board circuit, the stops of the Turing-Welchman-Bomb, which were also based on the random loops formation, were drastically reduced. The elimination procedure also applies to this control process through the diagonal board. The right solution is not sought, but the implausible results are excluded from further processing. Only when the diagonal board was built into the bomb would the Turing-Welchman-Bomb be ready for use. This table stands for the Blackboard connections of the Enigma in the example here in my lecture. 14 letters out of the possible 26 letters have been solved so far. The table continues to expand until all 26 letters have been solved. I want to summarize up to here. The search engine, the Turing-Welchman-Bomb, processes all possible 1,054,560 permutation addresses and tests each address with all possible 26 input letters. It is first tested whether a loop can be formed under each individual permutation address. If so, a further check is made as to whether the known graphical construct can be created under this permutation address and whether there is no implausibility. Sometimes, when processing all permutation addresses, there is only one plausible address. Most of the time, the search engine stops at several permutation addresses because then there is random no implausibility. The remaining permutation addresses must then be examined more closely. I could now start my microprocessor-controlled search engine. But my search engine automatically makes another decryption step that you had to do by hand in Bletchley Park. Before I start my search engine, I would like to explain the further decryption step. In Bletchley Park, this was done with a so-called checking machine. If the search engine has stopped, It is also known under which permutation address it has stopped. This means that all other permutation addresses around this stop address are also known. In the case of the crypt, all permutation addresses of all 15 scrambler for this crypts are known. If a letter is pending at one of the 15 scramblers, you can determine to which other letter it is permuted. In Bletchley Park, they use the checking machine for this. Here on this sheet of paper I have again shown the letters of the crypt and the letters of the ciphertext section opposite the crypt. The top row shows the letters that were typed one after the other on the Enigma. The bottom row shows the letters that are lit one after the other on the Enigma's lamp field as you type. In these adjacent rows and in these adjacent rows, the letters of the connector pairs that have already been determined and which have been swapped on the Blackboard of the Enigma are shown. These are then the letters that are applied to the scramblers for processing. But this time I used all the knowledge of the letters from this table. I have added a question mark to letters that have not yet determined. At this point in the table you can see that in contrast to this and this point, one letter is known to this scrambler. Under the permutation address BLF, you can see that one letter was determined on this scrambler. As you can see, it is the letter T on this scrambler. The permutation address and the determined letter are now entered into the checking machine, and the checking machine shows the other letter on this scrambler under this permutation address. In this case, it is the letter D. From now on, you know that the letters N and D on the Blackboard of the Enigma were plugged on with a cable. Another staggered letter pair has been identified, namely D and N. I apply this new knowledge here, here, and here. Now I also know, with the help of the checking machine, one letter on this scrambler. The permuted letter on this scrambler is the letter F. As a result, another pair of staggered letters is determined, namely the letters Q and F. In this scrambler, with the help of the checking machine, an N becomes the letter G. Thus, another staggered letter pair is determined, namely the letter pair G and H. Three more connector pairs have now been determined, namely the pairs D and N, F and Q, as well as the connector pair G and H. The Blackboard comparison table can be expanded accordingly. Up to now 20 letters out of the 26 possible letters have been determined. Everything that was determined here with the checking machine is made automatically by my microprocessor-controlled search engine. I programmed the appropriate algorithms for this. I would like to note here that my microprocessor-controlled search engine does a new test according to Gordon-Welchman's specification at this point with the extended Blackboard comparison table. Only if this test is also passed will the permutation address found by the Turing-Welchman-Bomb not be excluded. Now I want to start my microprocessor search engine. I have already entered the intercepted ciphertext with its 199 letters into my search engine. I have also already entered the crypt that I made up, namely Kommando der Wehr, in my search engine. All I have to do now is position the ciphertext correctly in relation to the crypt. I already planned that on this sheet of paper at the beginning. I slide the ciphertext past my crypt. With each shift step, the microprocessor calculates whether the position is even possible here and whether a loop can be formed here at all. I move the ciphertext so that it and the crypt are in the previously selected position. Using the algorithms I programmed, my microprocessor-controlled search engine designs automatically the best possible loop and tells me the number of possible boomers. The microprocessor search engine comes to the same result as what I have already designed manually with the small wooden sticks. A loop with 4 loop points and 6 boomers. The search engine successfully uses all 5 rotors for all possible 60 rotor arrangements. With each rotor arrangement, all 17,576 possible permutation addresses are processed, and that with all possible 26 input letters. The microprocessor-controlled search engine with the Zilog 8-bit Z80 microprocessor with 12 megacycles needs more than 4 hours for all these computing processes. That is about half a millisecond on a voltage for the calculation of a permutation address with one input letter. Therefore, I would like to present the search process in abbreviated from here. Now I start my search engine. You can see on the display that the engine is running and under which address it is currently looking. The search engine will stop under the following conditions. First, it must have found a loop. Second, the graphic that was created from the grep and the opposite ciphertext section and the graphic that results when a loop can be formed must not be implausible. What is meant here is the diagonal board by Gordon-Welchman. If there is no implausibility, a table can be created from the two graphics. This table can then possibly be expanded with the help of the checking machine. In the example here in this lecture, the table has been expanded by 3 pairs of letters. Third, this extended table is checked again using the Gordon-Welchman verification methods. Implausible results are then further excluded. All the functions that were carried out with the checking machine are carried out automatically by the microprocessor-controlled search engine I developed. Every time the search engine stops, I can look at the results on the display. Among other things, I can read off the unidentified letters, the no-plugged letters, and the determined pairs of letters. But the most important step is the automatic application of all letters determined up to this point from the stored comparison table. What was done with pencil and paper in Bletchley Park is done automatically by my microprocessor-controlled search engine. I programmed the appropriate algorithm for this. Under the permutation address at which the search engine stopped, the results from the comparison table are applied to the ciphertext section opposite the grep. If the complete grep is shown in plain text on the display as a result, the right search engine stop would most likely have been found. The rule is that the more correct letters are now in the grep, the greater the probability that the correct permutation address has been found. When the search engine is stopped for the first time under the permutation address Roman 143 IIX, there is no implausibility, but 3 letters in the grep cannot be resolved. Letters that cannot be determined using this comparison table are marked with a question mark. I make a note of this permutation address and continue the search process. The second stop is at the permutation address Roman 315 JLI. Here, three letters of the crypt cannot be resolved. Instead, there is a question mark here, here and here. I write down this permutation address and continue the search process. The third stop is at the permutation address Roman 341 WCE. Here, three letters of the crypt cannot be resolved. Instead, there is a question mark here, here and here. I write down this permutation address and continue the search process. The fourth stop is at the permutation address Roman 514 BLA. But something is completely different here. All letters of the ciphertext section can be converted to the crypt with the help of the comparison table. Everything is resolved here. It can therefore already be assumed that this permutation address is a correct permutation address. But not all possible permutation addresses have been processed yet. So I start the search engine again. The search engine stops again under the permutation address Roman 534 WYW. Even four letters cannot be resolved here. I also write down this permutation address and continue the search process. When the search engine has finished its search, it informs me of this on its display. Here I have summarized the results of the 5 search engine stops. There are no contradictions with any of the stops, but only with one stop can the assumed crypt be generated from the intercepted Enigma ciphertext section with the extended comparison table. It can be seen that only under the permutation address Roman 514 BLA are all 15 letters of the intercepted ciphertext section converted to the presumed text section, the crypt. That must now be the correct permutation address in the example here in my lecture. Up to this point in the decryption process, 20 of the 26 letters of the alphabet have already been identified. It is now known which 18 letters were plugged on the Blackboard of the Enigma. 2 letters have also been identified that were not plugged on the Blackboard. These findings are now applied to the entire text of the intercepted Enigma ciphertext with its 199 letters. Here on the display you can now see the results. Since the advance of the middle rotor and the left rotor are still unknown, all letters are processed with position middle rotor L and left rotor B. Therefore, only a maximum of 26 letters can be edited and displayed. Somewhere here in these rows of letters, the middle rotor or even the middle rotor and the left rotor must have advanced. Logically, after this point, correctly decrypted text can not longer be displayed. As a reminder, 6 letters have not yet been determined. For this reason, some letters in the text cannot yet be displayed. Instead, a question mark appears. Here is an example of that. First of all, it should be determined at which point in the text the middle rotor continues to turn. The advancement of a rotor other than the left-hand one was called turnover by the British. This was achieved by a ratchet and ball mechanism. The construction of the Enigma also included a feature known as double-stepping. This double-step feature was not an intended function. The mechanics just react that way. I don't want to explain how the mechanics work here. I'll just explain what it does. In the example in this lecture, the search engine where the complete crypt could be formed stopped with the insert rotors Roman 514. The rotor 4 was thus inserted in the right place of the Enigma. The transfer notch for the rotor Roman 4 is at the point of the letter K. Every time the right rotor Roman 4 changes from position J to K, the middle rotor is switched one step further. Check out this here. I put in another letter and the middle rotor has advanced one step. In the example in this lecture, the search engine with which the complete crypt could be formed stopped with the insert rotors Roman 514. The rotor 1 was thus inserted in the middle place of the Enigma. The transfer notch of the rotor Roman 1 is at the point of the letter R. Every time the middle rotor Roman 1 changes from the position Q to R, the left rotor is switched one step further. This is what is special about the Enigma mechanics. When you enter the next letter, not only will the left rotor and the right rotor advance, but the middle rotor will also advance one step again. Look what happened. All three rotors have advanced one step. The middle rotor was turned one step further twice in a row. Hence the name double step. Now it is important to recognize which text fragments make sense and which do not. To do this, you have to have a perfect command of the language in which the text is written. There were people like that in Bletchley Park. For example, there were German immigrants who had fled because of being persecuted by the Nazis. Or it was people who grew up bilingual. In any case, one must have good knowledge of the German language. First, a machine is needed that simulates the Enigma, including the Blackboard, but without automatic advance of the middle and the left rotors. The already determined 9 connector pairs in the example here in the lecture are given to this machine. Now any permutation address can be entered into the machine and the permutation at this address can be found out. The permutation address at which the search engine stopped is used. When the wheel order was Roman 514, the search engine stopped at the address BLA. This address BLA refers to the imaginary electrically acting rotor positions. That means the first letter in the crypt, the letter K, is permuted under the address A of the imaginary electrically acting right rotor. The rotors Roman 5, 1 and 4 from left to right are entered into the simulation test machine. If you now enter the intercepted encrypted ciphertext into the simulation test machine under the specification of Roman 514 and the start address BLA, the decrypted variant of this message then appears one after the other. It starts here at this point. The text that is created by permutation the letters of the intercepted encrypted Enigma ciphertext message makes a linguistic sense. Here in this case, Kommando der Wehrmacht. But at one point the decrypted message is just confused and no longer makes linguistic sense. This is the point where the middle rotor or even the middle and the left rotors must have advance on the Enigma. This point can be found out by turning the middle rotor or even the middle and the left rotors by hand at this point and observing whether the text makes sense again afterwards. In this example, in this lecture, the rest of the text becomes nonsense if the right rotor is at its imaginary electrically active rotor position address U. From this point on, there is only confused stuff. The following conclusions can be drawn from this fact. At this point, the notch must be on the alphabet ring of this rotor. In the example in my lecture, the text makes a linguistic sense again if the middle rotor is turned one step further at this point. If afterwards the text makes sense again, the right point for the advance of the middle rotor has been found. The search engine stopped with the wheel order Roman 514. The Roman 4 rotor has its notch unchangeable at the letter K. Please look here. The visible, readable alphabet ring must be on the letter K in this position. You can, from this letter K, add the letter sequence backwards. If the imaginary electrically active right rotor is in position A, the visible alphabet rotor is in the position Q. At the location of the notch, the letter of the imaginary electrically acting rotor is the letter U. In the same position, the letter of the visible alphabet ring is the letter K. Knowing this, the ring position of the right rotor can be calculated using the following formula. The ring setting is equal 27 minus the rotor position of the imaginary electrically acting rotor plus the rotor position of the visible rotor with the alphabet ring. At the position of the notch of the rotor, the imaginary electrical acting rotor carries the letter U. At the same position of the rotor with its notch, the visible rotor with its alphabet ring carries the letter K. In the counting method, the letter U stands for 21 and the letter K for 11. That gives the formula ring setting equal 27 minus 21 plus 11. The result for the ring setting is 17. And 17 represents the letter Q. But what is needed is the start position of the right rotor on its visible alphabet ring of the entire Enigma message, and not the start position of the right rotor in the crypt. From the notch point, one must follow the positions of the right rotor backwards. The entire Enigma message begins here at the letter J. But the starting position of the right rotor is the letter I and not J. Y is the starting position of the right rotor the letter I and not J, because with the Enigma pressing a letter key first causes the rotors to continue turning and only then does the permutation take place. An example: if the right rotor is in the position K and then the letter key W is pressed, the permutation of the letter W will take place under the address L of the right rotor. First comes the advance and then comes the permutation. Up to now, the starting position and the ring setting for the right rotor have been determined. The starting position letter of the right rotor is the letter I, and the ring setting letter of the right rotor is the letter Q. The ring setting of the middle rotor can also be determined using that method, but only if there is a double step in the Enigma ciphertext. But that rarely happens. In no case can the ring setting of the left rotor be determined in this way. I can also carry out these checks with my microprocessor search engine, but it is more convenient. I already had the intercepted Enigma ciphertext with the 199 letters entered into my search engine. Take a look at the display here. This is the result under the permutation address wheel order Roman 514 and the start address of the imaginary electrically acting rotor BKT. What I can see from the fragments in this example is that this stands for Das Oberkommando der Wehrmacht. In English, that means the High Command of the Wehrmacht. A maximum of 26 letters can be displayed decrypted. However, this is only possible if the maximum possible 26 letters are already in the comparison table, either as a staggered pair or as unplugged letters. If this is not the case, the display shows a question mark. Please look at this point. That's the case here. With my microprocessor-controlled device, I can simulate a simple advance of the middle rotor at any point of the text with a click on the Enter key. I can simulate a double step of the middle rotor if I double-click the Enter key on my device. If I simulate a step or a double step at a point in the text that turns out to be completely wrong, I can undo everything with the delete key. Since I, as a German, have a reasonable command of the German language, I can see that the text no longer makes sense from this point on. Or is it this point? I don't know at first. That's why I make a single click on the Enter key at this point in the text. Thus, an increment of the middle rotor is simulated at this point. This simulation of an advance of the middle rotor is then automatically repeated over and over again after another 26 letters. But what happened? Now the letters form a complete chaos. A double click also causes a similar situation at this point. So this cannot be the right position in the text. So I'll try again, but this time one position further. What happens this time? This is now a clear German word here, namely bekannt. In the English language this means known. It looks very good here. Oh, that's utter nonsense again. There must have been a double step in between. This must inevitably be 26 letters further after programming the first advance of the middle rotor. I move the cursor 26 positions further and then I double click the Enter key. Then I look at the letters of the whole text and I noticed that the word fragments that I can see make sense linguistically. Since the complete ciphertext now makes sense, even if a few letters are missing, the advance of the middle rotor and the left rotor is now determined by this procedure. I now know at which points in the text a simple advance of the middle rotor takes place and where a double step takes place. In the next step, the letters that have not yet been determined must be determined. This is done by adding missing letters in words that you are absolutely sure that this missing letter belongs in a word at this point. The missing letter is inserted into the word by pressing the letter key. Any new letter that can be inserted in the text also automatically expands the comparison table. An extended comparison table is then immediately applied to the entire text. But that doesn't work with every letter in a word. I would now like to explain why this is so. Because you know the permutation address at which the search engine has stopped, and you also know the positions in the text at which the middle rotor or even the middle rotor and the left rotor have advanced. You also know all permutation addresses in the entire text. The stated permutation addresses refer to the rotor positions of the imaginary electrically acting rotors. Every permutation address in the complete text is now known. With each permutation address you know how a letter is converted to another letter with the corresponding scrambler under this permutation address. To do this, at least one letter must be known to a scrambler. Look at this word. This word means Aachen, a German city in the far west. It is noticeable that the word Aachen begins with two letters A. But this just by the way. At this point where the question mark flashes, the letter C belongs. But when I typed in this letter, nothing happens. Why? The letter C has not yet been determined, neither as a Blackboard letter nor as a non-Black letter. That is the reason why the scrambler responsible at this point cannot be offered a letter. This is also the reason why neither an insertion of a letter here nor an expansion of the comparison table can take place. Different here with the German word abgewendet. In English this means averted. Without any doubt, the letter E is missing here at this point. The letter E has already been determined as a letter that has not yet been plugged on the Enigma Blackboard. If I type in the missing letter E here, the following will happen. Because the letter E is not plugged, the letter E will also go directly to the scrambler with the permutation address of the imaginary electrically active rotor position CQR at this point. At this permutation address, the scrambler converts the letter E to the letter I. At this point, there is also the letter I in the intercepted ciphertext section. It has now been determined that the letter I was not plugged on the Blackboard of the Enigma. I type the letter E. With this new level of knowledge, the comparison table will be expanded immediately. My microprocessor-controlled search engine applies this new knowledge immediately wherever possible. Look at this word in German Einsatz. In the English language, that means about mission. From a linguistic point of view, there is no doubt that the letter Z belongs here. I type in the letter Z and the table expands again. This extension immediately applied again to the complete ciphertext. Look at this German word der. That means the in the English language. The letter D is clearly missing here. I type it in and the comparison table expanded again and immediately applied again. Look at this German word und, that means and in the English language. The letter D is missing here. I type in the letter D and the table is expanded again. This extension is immediately applied again to the whole ciphertext. Finally, take a look at this German word gerettet. The word means saved in the English language. The letter T is clearly missing here. I'm typing in the letter T. As you can see now, question marks no longer appear in the entire text. All 26 letters of the alphabet have been determined. Now it is also known which 10 pairs of letters were swapped with each other on the Blackboard and which letters were not plugged. Now you can read the entire message in plain text. In German, the text in this example is called Das Oberkommando der Wehrmacht gibt bekannt. Aachen ist gerettet. Durch gebündelten Einsatz der Hilfskräfte konnte die Bedrohung abgewendet und die Rettung der Stadt gegen 18 Uhr sichergestellt werden. In English, that means the Wehrmacht High Command announces Aachen is saved. By bundling the military auxiliaries, the threat was averted and the town was rescued at around 6 p.m. At this point in the decryption process, one knows the plain text, the wheel order, the plug connections of the Enigma Blackboard, and the ring setting of the right rotor. In order to decrypt ciphertext messages as quickly as the production on the assembly line, the ring setting of the middle rotor and the ring setting of the left rotor are required. Since there is a double step in the text in this example, only the ring setting of the left rotor should actually be determined. But I would like to show the more complicated way here if there is no double step. Do you remember the beginning of my lecture? The German Schlüsseler simply came up with 3 letters for a starting position and 3 letters for typing into the Enigma. He made up these 6 letters at random and indiscriminately. These 6 letters were sent unencrypted into the air with the encrypted Enigma ciphertext message. I had also entered these 6 letters into my microprocessor-controlled search engine. The recipient of the Enigma ciphertext message needs these 6 letters to determine the starting position for his Enigma in order to decipher the ciphertext. The determination on the recipient side can only work if the recipient knows all other settings of the Enigma for this day. In order to carry out this determination, the recipient needs the wheel order, the ring settings of all 3 rotors, and the Blackboard connections. By this stage of the decryption process, the British had already determined almost all settings of the Enigma. What is still missing are the ring settings of the middle rotor and the left rotor. The middle rotor can take up 26 positions for the ring setting, and 26 positions can also be taken up for the ring setting of the left rotor. This results in 676 possible setting variants for the ring settings of the middle and the left rotor. One of these setting variants is always correct, the other 675 setting variants are always wrong. In the example in my lecture, the Schlüsseler receives an order from his superior to send a message. His Enigma is already prepared for this day with the correct valid settings. In this example in my lecture, the Schlüsseler first thinks up the letters B, P and F. These 3 letters were sent later unencrypted, and the Schlüsseler initially also used these 3 letters as the starting position of his own Enigma for this process, but only for determining the next 3 letters, but not for encrypting the Enigma ciphertext message. Then the Schlüsseler thinks up 3 more letters. In this example, the letters W, N and I. These 3 letters W, N and I will later become the starting position of his Enigma before the Schlüsseler encrypts the Enigma ciphertext message. He then types these 3 further thought up letters W and I one after the other into his Enigma. During this process, the letter lamps M, I, J light up one after the other. As already explained, these 3 letters M, I, J and the previous letters B, P, F are sent unencrypted with the Enigma ciphertext message. You have to know that so that you can understand what is next. Here is a description of the method to get further here. First of all 676 possibilities of the ring settings for the middle rotor and the left rotor must be tested. A modified Typex machine, model Mark 22, is used to determine these 676 starting positions. Enigma test rotors are used. These are inserted into the typex machine according to the already determined wheel order. The Blackboard of the typex machine is wired according to the connector pairs that have already been determined. The right rotor of the typex machine receives the already determined ring setting Q and the determined start position I. The tests start with the ring position AA for the middle and the left rotors and ends after 676 steps with the ring position ZZ for the middle and the left rotors. At the starting position for their typex machine, the operators set the three letters BPF, thought up by the German Schlüssler, for all 676 tests. As a reminder, these three letters were sent unencrypted. Then the operators of the typex machines typed in the next three letters MIJ, also thought up by the German Schlüssler. These three letters were also sent unencrypted. The operator does this with all possible 676 ring positions for the middle and the left rotors. The letters MIJ are typed in for each test step. As you type in the three letters MIJ, three letter lamps light up one after the other. These three letter lamps that light up one after the other are written down. The respective ring settings are also written down. When the job is done, the 676 ring positions and the associated 676 letter combinations, consisting of three letters that are lit one after the other, are on sheets of paper. One of these 676 records is the correct setting of the Enigma. But which of the 676 records is correct? The first Enigma ciphertext message that day had already been determined during the decryption process. Now here is the key to solving the problem. The 676 records are then tested with further modified typex machines. These typex machines also receive the same specifications as the previous typex machines with regard to the Blackboard connections and the wheel order. The right rotor of the typex machines is also set with the settings already determined for the ring position and the start position. The 676 setting possibilities for the ring settings of the middle and the left rotor are also set one after the other on these typex machines. In the previous step, the three letters were recorded for each individual possibility for the ring position in the order in which the letter lamps were lit. These three record letter combinations have completely different values for each of the 676 possibilities. These 676 letter combinations, consisting of three letters recorded in the previous step, are now tested one after the other as the start positions for the 3 rotors. One of the 676 records is the correct one, in which when you type in the letter sequence K, T, J, P, H, Q, H of the intercepted Enigma ciphertext, the letter lamps D, A, S, O, B, E, R light up one after the other. The correct starting positions and the correct ring settings for the middle and the left rotors are found now. With the start position W and I and the ring settings V, D, Q, you get the same decrypted text with an Enigma as before with the search engine. Do you understand now why about 7,000 people were employed in Bletchley Park? My microprocessor-controlled search engine goes through all 676 possible ring settings and then reports at which ring setting the same plaintext is obtained as the already known plaintext. These settings are then shown here on the display. In this display step, I can print out all the relevant results. I press the printer button and the printer starts printing. Here is the overview of the printout. First, the 3 rotor positions of the imaginary electrically active rotors are printed out at which the search engine stops. Then the wheel order under which the search engine stopped is printed out. Then the determined stacker pairs of the Blackboard are printed out. Then the start position and the ring settings of the real rotors of the Enigma are printed out. The printout is made alphabetically and numerically. Then the plain text is printed out. The following must be noted about this printout. Here the word Aachen. What is meant is the city. The city name is sent twice. According to the Army Service Regulations, proper names had to be sent twice and enclosed with an X. A time is written here. Numbers in the text were written out as words. Each number written out had to be enclosed with the letter X as well. This is the end of my lecture now. I think I have clearly shown how the British managed to determine from an intercepted Enigma ciphertext message all the setting data that were necessary to decrypt all following Enigma ciphertext on that day. I can only say chapeau. The work that has been done in Bletchley Park is absolutely exceptional. How difficult the whole thing is, I only realized after I had built my own microprocessor-controlled search engine. The whole thing was very arduous, but gave me a lot of joy. Thank you for your interest in this lecture, and I say goodbye with kind regards from Germany.